There is probably no thought experiment in the history of science that has been more widely referenced, more frequently misunderstood, and more thoroughly dragged into conversations it was never meant to be part of than Schrödinger's cat. You have seen it on t-shirts. You have heard it used to justify all manner of vague philosophical claims about reality, observation, and consciousness. It has appeared in movies, television shows, and countless pop science articles, usually as a shorthand for the idea that quantum mechanics is simply weird and that anything goes at the quantum level. But here is something important. Erwin Schrödinger did not devise his famous thought experiment to celebrate the strangeness of quantum mechanics. He devised it as a criticism, a reductio ad absurdum, to show that something must be incomplete or wrong about the way quantum theory was being interpreted at the time. Today, we are going to explore what Schrödinger's cat actually means, what it was actually arguing, and, most importantly, for this channel, what it genuinely tells us about the principles that make quantum computing possible. First, let us set the scene properly. In 1935, Erwin Schrödinger, one of the founding architects of the quantum mechanics, and the man whose equation describes how quantum states evolve over time, published a paper that contained the thought experiment that would make his name famous beyond physics. He was engaged in a debate with the dominant interpretation of quantum mechanics of his day, known as the Copenhagen interpretation, associated primarily with Niels Bohr and Werner Heisenberg. The Copenhagen interpretation held, roughly speaking, that quantum systems do not have definite properties until they are measured. Before measurement, a particle exists in a superposition of possible states. Measurement causes the wave function, the mathematical description of the quantum state, to collapse into a single definite outcome. The act of observation, in this framework, plays a fundamental role in determining the state of reality. Schrödinger found this deeply unsatisfying, and his thought experiment was designed to expose what he saw as its absurdity. Here is the setup. You place a cat inside a sealed box. Also inside the box is a tiny amount of a radioactive substance, a Geiger counter to detect radiation, a vial of poison, and a mechanism that will shatter the vial and kill the cat if the Geiger counter detects a radioactive decay event. Radioactive decay is a quantum mechanical process. According to quantum mechanics, after a given period of time, the radioactive atom exists in a superposition of having decayed and not having decayed. If the Copenhagen interpretation is taken seriously at the macroscopic level, this superposition propagates up through the chain of cause and effect, through the detector, the mechanism, and ultimately to the cat itself. The cat, by this logic, would be in a superposition of alive and dead, right up until someone opens the box and looks inside. Schrödinger's point was not that the cat really is both alive and dead. His point was that this conclusion is absurd, and that therefore the Copenhagen interpretation must be missing something. He was using the cat as a rhetorical device to argue that there must be some boundary, some rule that prevents quantum superpositions from scaling up to the world of everyday objects. He was right that this is a genuine and deep problem in the foundations of quantum mechanics. It is called the measurement problem, and physicists and philosophers of physics are still actively debating it today. Different interpretations of quantum mechanics, the Copenhagen interpretation, the many worlds interpretation, decoherence-based approaches, and others, all offer different answers to the question of why we do not observe cats or any macroscopic object in superpositions. The most widely accepted practical answer among working physicists today involves a process called decoherence. When a quantum system interacts with its environment, the air molecules around it, the photons hitting it, the vibrations passing through it. It becomes entangled with an enormous number of external particles almost instantaneously. This entanglement effectively destroys the observable coherence of the superposition at the macroscopic level. The cat is not in a superposition in any practically meaningful sense, because the quantum information about its state leaks into its environment faster than you could ever hope to measure it. Decoherence does not fully resolve the philosophical measurement problem. That remains contested. But it explains why we never see cats, tables, or people behaving like quantum particles in our everyday experience. Now, here is where all of this connects directly to quantum computing, and this is the part that most popular accounts of Schrödinger's cat never get to. The same process of decoherence that prevents Schrödinger's cat from genuinely being in a superposition is the single greatest practical obstacle facing quantum computing today: qubits. The quantum bits that quantum computers are built from must maintain their quantum superposition and their entanglement with other qubits long enough to perform a computation. But qubits are physical systems, and like any physical system, they interact with their environment: heat, vibrations, stray electromagnetic fields, even the act of trying to measure or control the qubit. All of these interactions cause decoherence. When a qubit decoheres, it loses its quantum properties and behaves like a classical bit. The quantum computation is ruined. This is why quantum computers must be operated at temperatures colder than outer space, just fractions of a degree above absolute zero. At those temperatures, thermal noise is reduced to the absolute minimum. This is why quantum processors are housed in elaborate shielded enclosures. This is why quantum computing researchers spend enormous effort on materials science, engineering, and quantum error correction, all in service of keeping their qubits coherent for just a little bit longer. The time during which a qubit can maintain its quantum state is called its coherence time. And extending coherence time is one of the central engineering challenges of the entire field. Modern superconducting qubits, the kind used by IBM and Google, have coherence times typically measured in microseconds to milliseconds. That sounds short, because it is. Researchers are working hard to extend it. Schrödinger's cat also connects to the concept of quantum error correction in a subtle but meaningful way. The thought experiment illustrates that quantum information is extraordinarily fragile. It collapses, it leaks, it decoheres. Quantum error correction is the science of protecting quantum information from exactly these kinds of collapses, using clever encoding schemes that spread quantum information across many physical qubits in such a way that errors can be detected and corrected without directly measuring the underlying quantum state and destroying it. This is technically demanding work, and achieving the scale of error correction needed for a fully fault-tolerant quantum computer is one of the defining challenges of the next decade of quantum research. So the next time someone uses Schrödinger's cat as a vague metaphor for uncertainty, or the idea that reality is whatever you want it to be, you will know better. The cat was not a celebration of quantum weirdness. It was a serious scientific argument about the foundations of physics, one that pointed directly at problems that are still being worked on today. And those problems, decoherence, measurement, the fragility of quantum states, are not abstract philosophical puzzles. They are the very obstacles that engineers and physicists are fighting against every single day as they try to build the quantum computers of the future.